Hello students. So today we are going to discuss error function. This is third type of the function, beta, gamma, and this one is third. This is also called probability integral because it is used in probability theory. So definition, we are going to discuss here definition of error function, its complement, and some properties of error function. So we go with the definition. Error function of x, it is defined as 2 upon root pi 0 to x. This is a type of the integral with limits 0 to x e raised to minus t square dt, and its complement is defined as 2 upon root pi x to infinity e raised to minus t square dt. Now you can write down error function as in this form also, 2 upon root pi 0 to x e raised to minus u square du also. That is, if you change the variable, it does not change the value. Similarly, if you would like to write down error function of a, then it would be something like this, 2 upon root pi 0 to a e raised to minus t square dt and so on. Similarly, for complement also, the same thing it is there. If you change the variable, it is e raised to minus u square, e raised to minus y square and so on. Now, if you try to draw the graph of this function, it would be something, the graph, it is some, I take the point 0, 1 here, then here 0, minus 1, this is x and this is error function of x or complementary error function of x. Error function of 0, it is 0, so it would be something like this, it is asymptote. Error function of infinity is equal to 1 and something like this. Similarly, complementary error function of x is this. So this is error function of x and this one is complementary error function of x. So this is complementary error function of x. So actually these are the notations used, and we discussed few properties here. Error function of 0 is equal to 0 from the graph. If you observe, it is origin, this is origin. Error function of infinity is equal to 1, it is this. Sum of the error function and its complement is always equals to 1. So you can prove this. If you would like to, this also it can be proved. Error function of x, if you add these two together, then it would be error function of x plus complementary error function of x. This is equal to, if you take the integral, 2 upon root pi 0 to x e raised to minus t square dt plus 2 upon root pi complement x to infinity e raised to minus t square dt. Now by using the properties of definite integral, you are having something like this. It is 0 to infinity e raised to minus t square dt, and value of this particular integral, this is standard integral and its value is root pi upon 2. So that's why value of the error function and its complement is always equals to 1. Similarly, error function is an odd function. That is, error function of minus x is equal to minus error function of x. So error function is an odd function. So this can also be proved. So these are some properties of error function. Now we shall see some applications, some illustrated examples on error function. So the first example here, it is first example, show that a to b e raised to minus x square dx, this is equal to root pi upon 2 error function of b minus error function of a. Now to prove this, you can consider either RHS or LHS. If you consider LHS, you have to split the integral from a to 0, 0 to b. Or if you consider RHS and try to show LHS, so RHS is this this is equal to root by pi upon 2 error function of b minus error function of a. So I use the definition of error function. It is root of pi by 2. Error function of b is 2 upon root pi 0 to b e raised to minus t square dt minus error function of a is 2 upon root pi 0 to a e raised to minus t square dt. So I take common 2 upon root pi. So root pi upon 2 into 2 upon root pi. Inside the bracket, it is 0 to b e raised to minus t square dt and minus 0 to a. I make it plus and change the sign. A to 0 e raised to minus t square dt. So a to 0, 0 to b, we can write down this gets cancelled as a to b e raised to minus t square dt, or you can write down this as a to b e raised to minus x square dx, and that is your LHS. So this is the way you can prove these identities over here based on error function. Now next example on this second error function, second error function of x plus complementary error function of x plus complementary error function of minus x, this is equal to 2. This is another identity here. So we can prove this, show that it is, I consider the LHS, consider LHS complementary error function of x plus complementary error function of minus x. So I call this is 1. Now I use the property, we have error function of x plus complementary error function of x, this is equal to 1. Therefore complementary error function of x is equal to 1 minus error function of x. So I call this is 2. Now similarly I would like to get the expression for this. So I replace here, put x is equal to minus x in order to have this particular expression here. So I put replace x by minus x in this expression. So error function of minus x plus complementary error function of minus x, this is equal to 1. Therefore complementary error function of minus x, this is equal to, this is minus error function of x because error function is an odd function. So I just write down, or I just write this as minus error function of x first and then plus complementary error function of minus x, this is equal to 1. So or complementary error function of minus x is equal to 1 plus error function of x. So this is 3. I substitute from 2 and 3 in 1. So LHS is equal to, this is equal to complementary error function of x plus complementary error function of minus x, this is equal to complementary error function of x is 1 minus error function of x from 2, and from 3 complementary error function of minus x is something 1 plus error function of x. So error function of x. So this gets 1 plus error function of x. So this gets cancelled from here and you are getting the value of this, it is 2. So we proceed further for the next example on this error function. Next example, it is this, show that, third one, show that 0 to infinity e raised to minus x plus a bracket square into dx. This is equal to root pi divided by 2 1 minus error function of a 1 minus error function of a. Solution, I consider LHS or RHS. Consider, let I is equal to the integral LHS, it is 0 to infinity e raised to minus x plus a bracket square dx. Now what is the technique? If you observe the error function, so error function of x, it is something like this 2 upon root pi 0 to say x e raised to minus t square. So this is the kernel driving function. So I must get this driving function here by putting x plus a is equal to t. That is the technique used to select or choose the substitution. So I put x plus a is equal to t. Therefore, dx is equal to dt. Dx is equal to dt. And what about the limit c? If you put x is equal to 0 here, so x is equal to, for x is equal to 0, t is equal to a, and for x is equal to infinity, infinity plus a, t is equal to infinity. So limits new for this is a to infinity. Therefore, integral I will have the form a to infinity e raised to minus t square into dt. Now these are the limits naturally for the complement. Only thing is that 2 upon root pi, it is missing here. So I just multiply and divide by 2 upon root pi. So a to infinity e raised to minus t square dt, and this is only missing for the complement. So this bracketed part is, it is root pi upon 2, and this is complementary error function of a. This is complementary error function of a, and this is equal to again root pi upon 2. This is actually by using sum of the error function and its complement is 1. So I can write down this as 1 minus error function of a, and that is what your RHS required over here. So like this, you have to use the suitable or proper substitution over here and get or evaluate this kind of the integrals. We proceed further for the next example on this error function. Next example, if alpha x, problem number 4, if alpha x is equal to root 2 upon pi 0 to x e raised to minus t square by 2 dt, then show that alpha x root 2, this is equal to error function of x. Alpha x root 2 is equal to error function of x. So simple technique here, again the same solution. It is given error function of alpha x, this is equal to root 2 upon pi 0 to x e raised to minus t square by 2 into dt. So what I do here, so I would like to prove this. So I replace, put x is equal to x root 2. So I would like to prove here this. So I replace here alpha x root 2, this is equal to root 2 upon pi, then 0 to x root 2 and e raised to minus t square by 2 dt. Now I would like to reduce this to error function of x. So error function of x, again I move to the kernel driving function. So it must be of this particular form. e raised to minus x square. So of this particular form. So I must substitute here, put t square by 2 is equal to x square. So like this. So x square, so or u square, x square, e raised to minus u square, t square, anything you can take. So t square is equal to 2 times u square. So t is equal to root 2 into u. And what about the limits? For t is equal to 0, u is equal to 0, and for t is equal to x root 2 over here. So root 2 gets cancelled, u is equal to x. So you are getting limits, u is equal to x. So with these limits I get transform this 2 upon root pi 0 to x e raised to minus u square, and dt is root 2 into root 2 dt is what? Dt is not calculated here. Dt is equal to root 2 into du. Naturally, if you take the differentials, it is this into d. Now, this root 2 and this root 2, it is 2 divided by root pi 0 to x e raised to minus u square du, and this is error function of x. So, error function of x, so alpha x root 2 is equal to error function of x. Alpha x root 2, that is alpha x root 2 is equal to error function of x, and hence this is proved here. So we go for the next example on this error function. Next example on error function, show that d by dx of error function of ax, this is equal to 2a upon root pi e raised to minus a square x square, So derivative of the error function. So how to find derivative with respect to x, with respect to a of the error function? That is what the problem is all about. So I just define error function of x first. Error function of x, we have, it is something like this, 2 upon root pi 0 to x e raised to minus t square dt. Now error function of ax, therefore x is replaced by ax, this is equal to 2 upon root pi 0 to ax e raised to minus t square dt. Now we have to find derivative of this. So means dash error function, we have to find out this error function of dash of x with respect to x, means x is parameter we take and we use. So in this case we are using DUIS second rule because limits are depending upon the parameter. Using DUIS, see what happens, second rule. So d by dx of error function of ax by considering x as parameter, x is parameter, and second rule x parameter. So what is happening here, see, 2 upon root pi, I just write this 0 to ax dabba by dabba x of e raised to minus t square dt plus d by dx of upper limit, it is ax, and the integrand where t is replaced by upper limit x bracket square and minus lower limit d by dx of the derivative of lower limit, that is 0, and hence next would be 0. Just you have to simplify this, it is 2 upon root pi. Now derivative of x, this is independent of x with respect to x, keeping t as a constant, so not containing x, so naturally this is 0 here, 0, plus this is a here and e raised to minus a square x square. So and last term is 0. So you are getting this as this 2 into a, this is 2a upon root pi e raised to minus a square x square, and that is what the RHS here which is required. Similarly, you can just see with respect to a also, you are just integrating a means you are getting this 2x upon root pi and so on. Similarly, show that error function of root t d by dt of error function of root t, this is equal to e raised to error function of root t is equal to e raised to minus t divided by root of pi into t. This also same technique it is to be used. So we take parameter as t there, d by dt. So error function of root t, solution, error function of x, it is again we take 2 upon root pi by basic integral of error function 0 to x e raised to minus u square I take here du, because t is already involved. So therefore error function of root t, replace x by root t, 2 upon root pi 0 to root t e raised to minus u square du. Okay, so d by d using again t is parameter, dy is second rule, t is parameter. So what is happening, see, if t is parameter, d by dt of error function of root t, this is equal to 2 upon root pi inside the bracket 0 to root t dabba by dabba t of e raised to minus u square du plus d by dt of upper limit, it is root t, and multiplied by wherever u is there, it is replaced by minus root t bracket square, and lower limit as usual it is 0 there, so need not be considered the next part. So you are getting 2 upon root pi, the next step, so this would be 0 because with respect to t, independent of t, partially with respect to t would be 0. So 0 to root t, this is 0 into du, plus this is 1 upon derivative of root t is 1 upon root t into e raised to minus t, and next would be this 2 may be getting cancelled from here, and you are getting 1 upon root pi into t e raised to minus t. That is what required here, that is the RHS. So this is the way you can just find out these things. Similarly, find next example is find d by dx of complementary error function of ax, d by dx of complementary error function of x. You can find out this. So these are all derivative based problem on error function, derivative of error function. So you have to find out this complementary solution. We have error function of x, or ax I take directly, complementary error function of ax, it is 2 upon root pi ax to infinity e raised to minus t square dt. We just take x first, complementary error function of x, it is x to infinity e raised to minus t square. So put, we need to find this, so put x is equal to ax. So what happens, see, therefore complementary error function of ax is equal to 2 upon root pi ax to infinity e raised to minus t square dt, e raised to minus t square dt. Now I just take again parameter. Suppose I would like to find with respect to a, then a is parameter, it is with respect to x, so x is parameter. Using DOIS second rule with variable limits by x as a parameter. X is parameter. So what happens if it is required d by dA? A is parameter. So what happens? See, d by dx complementary error function of x. This is equal to 2 upon root pi ax to infinity dabba x of e raised to minus differentiation under the integral sign into dt plus d by dx of upper limit, it is infinity, multiplied by e raised to minus infinity bracket square minus lower limit d by dx of lower limit is x into e raised to minus ax bracket square. So this is 2 upon root pi. So naturally this would be 0 again. So this is 0 plus this is also 0, and last one is this is with respect to x means a you are getting e raised to minus a square x square, and finally you are getting this as this 2 minus a means minus 2a upon root pi e raised to minus a square x square. So this is your d by dx of complementary error function of x. Okay, so that's all about the error function of x.